Okay, hi everyone. Thanks for coming to this week's seminar. Jan is now going to introduce our speaker for today.
Hi everyone. I am very pleased to host today Amy Ryan, who will be speaking to us about the rheology of bubbly magma and how outgassing takes place. Amy is long known now in the experimental volcanology community. She started a degree in 2006. So she did a bachelor at the University of Colorado College, working with Steve Kwan and Christine Sedoway. And then went on to the University of British Columbia to work with Katie Russell and other at the University of British Columbia. And she worked on the solubility of water and magma, amongst other things. And then went on to do a PhD on the timescales and the consequences of solid state diffusion during sintering in volcanic systems. She's very well versed with how to use experiments to think about volcanic systems, and we're going to see some of this today. And amongst other things, I'd like to point out she was the winner of the gold medal of the Canadian Association of Geology. So congratulations for this.
Thank you.
And now she's at the University of Minnesota on an NSF grant to study magma, essentially genesis, and also the removal of magma from these crystal-rich mush or aggregates in the earth. So looking at the lower part of magmatic system. So the floor is yours, and I look forward to your presentation. Thank you.
Thank you very much. Hi, everyone. Thank you for the invitation to speak today, and thank you for that introduction. Before I begin, I'd like to quickly acknowledge my collaborators on some of the work that I'll be presenting today. These include Kelly Russell, Stefania Sicola, Alessandro Vona, Mike Heap, Stefan Kolzenberg, Claudia Romano, Alex Kushner, and Steve Badger. Okay, so for the next 30 to 40 minutes, I'll be talking about research I've conducted to try to answer these three research questions. What's the viscosity of a bubbly melt? When and how do bubbly melts outgas? And what's the relationship between rheology and outgassing? Volcanology folks in the audience will recognize these as questions that the field has been trying to answer for 50 years. So it might not be surprising that my final slide is that there's still lots to do. Nonetheless, I'd like to show you some novel new results that sort of push us forward in answering these bigger research questions. And this body of research is really motivated by the fact that volcanic eruption style and lava flow dynamics are ultimately controlled by the volume and pressure state of gases trapped in the volcanic system. And I have a few examples I'm going to walk through here just to illustrate that and really enforce that we need to know how rheology and outgassing work in bubbly melts and how they sort of interact with one another. So on the left is a schematic showing how we think eruptions may occur in some silicic systems. I'm going to be focusing on silicic systems for the remainder of this talk, but there are sort of crossovers with other melt compositions. Magmas that contain trapped gas-filled bubbles are more likely to erupt explosively, but if that gas can sort of be vented out of the system away from the melt component, we're more likely to get an effusive eruption of that melt phase. So in the schematic on the left, envision that there's a bubbly melt that's rising, and at about 1 kilometer depth, deformation of that melt causes the creation of permeable pathways. And those permeable pathways essentially bleed off all of the gas components to the surface, where they experience sort of energetic jetting, and we have these nice sort of plume cartoons drawn. Meanwhile, the melt that's now been relieved of its gas component can sort of diffuse across the surface more quiescently. As another example, I have here an aerial image of Little Glass Mountain, which is a silicic lava flow in the United States. Note its quite large aerial extent. The composition of the melt component in this lava flow would have a very high viscosity at its eruption temperature. So it would be very difficult if the melt alone was moving across the surface to achieve a flow sort of this extent. So the way that we reconcile high melt viscosities and large aerial extents we observe for many silicic lavas, not just Little Glass Mountain, is to imagine that the lava was actually populated with bubbles at the time that it erupted on the surface. That bubble content reduces the effective viscosity of the material as it flows, allowing us to get these sort of bigger flows. And when we go in the field and actually look at the materials that are preserved, we do see some very vesicular regions, but there are also thick bands of dense obsidian, which evidence regions when the material was still hot, where there were essentially no bubbles present and it was only melt. As a last example here, I have a map of another silicic lava flow in the United States. And what are shown on top here and labeled with letters are mapped explosion pits. Note their distance from the vent, which is shown here as a star. And these explosion pits evidence pressurized gases being trapped throughout the flow of the lava, even quite a distance from the vent itself. And then as the lava begins to slow or even stall, those pressurized gases will accumulate and eventually strain the surface of that cooling or even solidified lava faster than it can relax, creating these explosion pits that we can later go map. So these are 3 examples, but certainly not comprehensive, to sort of show why we need to study rheology and outgassing of bubbly melts. So I'm going to start now with the viscosity of bubbly melts. This is where I'll focus for a lot of the talk because it's quite complex, as you'll see. As I said, this has been an area of study for about 50 years. So as such, there are numerous experimental studies that have been conducted to try to constrain the relationship between porosity and relative viscosity for silicate melts. But you'll note right away that we have diverse experimental results. At the most extreme, materials of the same porosity have measured viscosities that are 2 orders of magnitude sort of different across studies. I've also plotted on here 2 semi-empirical models, and you can see in some cases they do a good job of describing the data, and in some cases they don't do a great job, and in some cases they're entirely unconstrained. So I want to take a first crack at trying to understand why we're getting these diverse results. And I would suggest that we do that by thinking about the pore geometry in the materials that have been used in these experimental studies. This is a figure I love, showing the diversity of pore space geometries that we can expect in volcanic materials. And not only does it do a great job of allowing you to see the full range of geometries we can expect, you can sort of infer from these images that connectivity of pore spaces varies widely across these materials. And as such, some are more likely to accommodate gas escape and others will suppress any sort of gas loss or outgassing just by the nature of the pore space geometry alone. So let's take 2 extremes. The top one here represents volcanic melt particles that have begun to sinter together, but host abundant intergranular space. And you can sort of visually assess that the intergranular space here is quite well connected. In contrast, the image on the bottom here represents a melt that is vesiculated, so grown its own bubbles. And while those bubbles may communicate with 1 or 2 other bubbles around them, overall the connectivity of the pore spaces is quite low. To bring in the rheology side, because that's a majority of what I've worked on, now let's imagine compressing each of these materials. On the top, if I were to compress the K schematic here, and let's just call it uniaxial compression, so the sides are unconstrained. You can imagine that as I compress, the pore fluid that fills that intergranular space will be sort of evacuated or sort of purged out the sides as a result of compression. So if I'm measuring mechanical, or if I'm collecting mechanical data during compression and I'm calculating from that a viscosity, that viscosity is telling me something about the melt framework, but it's also telling me something about how easy it is to collapse the pore spaces. In contrast, if I try to compress the material on the bottom, B, you can imagine as I'm compressing, the pore space doesn't really, or the pore fluid in those bubbles doesn't really have the same opportunity to escape from the system because of the low connectivity. So any viscosity I calculate when measuring something like this will reflect the melt framework again, of course, but will also tell me something about the resistance of the bubbles and the gases trapped therein to compression. If I steal some terminology from material science, we can call the material on the top open cell and the material on the bottom closed cell. So as a first pass, can we understand the diversity of the experimental results that we have so far by looking solely at pore geometry. So I've sort of colored this or coded it to reflect the different geometries. The open diamonds are more like this material K, and the black bars or black circles are more like material B. And what you see is that this geometry or the separation by geometry doesn't quite answer why we have such a diverse range of results. And part of that, I would say, is because of the flaw in the way that I've just set up this thought experiment for you, which is equating this bubble geometry with inherently being closed cell. And I'll show you why that's a problem now. Stefania Sikola completed her PhD at Roma Tre, and in her PhD, she was studying the viscosity of bubbly melts. So in these experiments, she would heat a water oversaturated rheologic glass above the glass transition. That would cause it to foam, so to vesiculate and be populated with bubbles. And then she would compress the material under a small load to relatively low strain. And she had two experiment subtypes, one so-called double stage experiments and one a single stage experiment. And this double stage was mimicking a method previously used by Vona et al. 2016. In these double stage experiments, she would heat the core, allow it to foam for some extended period of time, and then rapidly quench it below the glass transition back to room temperature. The material would sit at room temperature and room pressure for 15 days, and then she would reheat it, load it, and deform it. In the single stage experiments, she would do all of these steps in one go. There's no quenching that's occurring here. And what she measured are different viscosities for these two subtypes of experiments. You can see the single stage data are the open symbols here, and the double stage data are the closed symbols throughout. Note that in every other figure I'm going to show you that has a viscosity on the y-axis, it's going to be a log scale. This is the only one that's linear, but that's why the distribution of data looks a little bit different. So she was understandably perplexed as to why the single stage data and double stage data don't sit in the same sort of regime or region in this viscosity and porosity space. The samples look the same, they have the same pore geometry, they're vesiculated melts. And helium pycnometry, a technique that we often use to look for connectivity of pore spaces in experimental or natural materials, didn't show any difference in connected porosity between the two experiment subtypes. So what she did then is she did the first stage of her double stage experiment. She heated the sample, allowed it to foam, quenched it, and then instead of deforming it, she cut it open and looked at it in the SEM. And what she observed was a series of microcracks, very, very fine microcracks, extending between the bubbles and out to the surface of the core. The microcracks are shown here with red arrows. So her interpretation of these microcracks is that they form during that quenching process when crossing the glass transition. And ultimately, the formation of these microcracks now allows the pore fluid that was held in that bubble to leak out of the system without us even really detecting it. So her interpretation overall is that the reason that we have the difference between the single stage and double stage materials is because they're inherently different. One has a higher viscosity because it's populated with a gas-filled bubble. It is a closed cell material. And the other one, while masquerading as closed cell, is actually populated with these drained pores and was open cell at one point. This is consequential because it means that microcracking, whether as a result of cooling across the glass transition or by being strained faster than the material can relax, again, crossing the glass transition, changes magma viscosity even if the porosity of the material is exactly the same. That's shown graphically here, where there are two separate viscosity porosity paths, one defining bubble growth, so where you're populated with gas-filled bubbles, and one where those bubbles have been drained of their pore fluid. So this is a sort of critical thing to note when thinking or when trying to, again, understand what the viscosity of a bubbly melt is. You got to make sure that you're actually working on a bubbly melt, which is not necessarily obvious. So if I put Stefania's data back into this data summary, the blue circles here are her gas-filled bubbly melts, and these black ones here are the drained melts populated with drained pores. And all of the gray symbols here are the samples I showed earlier that have the same geometry as Stefania's work. We can't necessarily say whether they were filled with bubbles or pores at the time of deformation, because often the experimental methodologies included some quenching stage. So still lots to do. Coming back to my final slide. So while Stefania was working on all of this, I wanted to know what happens over here in this red region where there's no data. And it's worth noting that above porosities of about 0.74, 0.75, which is delineated by this box, the material is better described as a foam than a suspension, which is more applicable to porosities below 0.74. Nonetheless, magmatic foams happen in nature, so it's worth knowing what's happening over here in this region. In order to conduct experiments here, though, I needed a closed cell glass or melt foam to work with. And luckily, that's something that's actually industrially produced. So for my experimental work here, I used a closed cell glass insulation called foam glass, which is produced by Owens Corning. The solid component of this insulation is a soda lime glass that contains a little bit of iron in it. So it actually oxidizes when exposed to the atmosphere at high temperature. The initial porosity of this material is 90%, and it has a relatively restricted bubble size, as you can see from the XCT image here on the left. In contrast to Stefania's experiments or previous experiments that have been conducted where the pore fluid is water, here it's CO2. That's notable because the solubilities of those two volatile phases are quite different. Water has the potential to resorb back into the melt or to diffuse out of the system, whereas the low solubility of CO2 means it's sort of trapped in space. The last really cool feature of foam glass is that it's initially impermeable, despite its very, very high porosity. So I conducted a series of high temperature deformation experiments using this uniaxial compression rig shown in the bottom left. I cored a bunch of foam glass samples, and I would heat them above the glass transition, which is why their color changes here, and then deformed them to variable axial strain from 0.5 to 0.05, sorry, to 0.6 at 2 different strain rates. And I measured load and displacement throughout deformation. These are the mechanical data I collected during my experimental campaign. There's a lot going on here, but that really speaks to the complex response of the material to compression. I observed viscous flow indicated by these smooth curves that you see in a majority of the panels, as well as fracturing indicated by these stress drops in some particular panels. I also observed strain weakening indicated by a negative slope for these mechanical data curves, as well as strain hardening, which is a positive slope that you see throughout. You might not be able to immediately see this, but I'd like to assure you that the deformational behavior changes systematically in this system or in this material as a function of strain rate and temperature, which is to say melt viscosity. To summarize, at low strain rates and or low melt viscosities, I tended to observe viscous flow with limited strain weakening. So a curve like these ones would be representative, or these red ones at the bottom. At high strain rates and or high melt viscosities, I tended to observe fracturing and a greater magnitude of strain weakening. So representative curves would be some of these ones here or these ones over here. Because I know deformational behavior is inherently linked now to strain rate and melt viscosity, I wanted to combine those two things into a single parameter just to make my life a little bit easier and get a better chance of interpreting what's actually going on in this material. So I reframed strain rate and melt viscosity into a single parameter, the Deborah number, which in this case represents the melt relaxation state. So what I can do then is I can put all of my measured viscosities onto a single plot and interrogate them this way. And what I observed is using the mechanical data and calculating viscosity, viscosity increases with strain, but decreases with increasing Deborah number. Note that strain rate and melt viscosity increase going this direction. A Deborah number of 10 to the minus 2 has previously been defined as a sort of delineating a regime where materials are relaxed or unrelaxed. It's previously been described even as a viscous brittle transition. And so I've colored it in gray here. And what you observe is the samples where I observed fracturing, noted here as X's, all occur where Deborah numbers are greater than or equal to 10 to the minus 2. So that makes sense, no aberrant behavior, which is great. Many other of the sort of observations I made about my cores and about their mechanical behavior and other things, they're all tied actually to the Deborah number. And I'll give you some examples now. The core shape, for example, changes systematically with Deborah number. Materials deformed or cores deformed at low Deborah number conditions tended to barrel, whereas those deformed at high Deborah numbers sort of compacted in their own footprint. And I should say that the upper and lower diameter of these cores doesn't change significantly from the initial diameter of the core before deformation. Now I did a little bit of trickery here, and I calculated the core volume based on the core shape, and then I used that to try to understand what a pore in the core might be experiencing. So in that way, I can estimate the change in pore volume as a result of strain, which makes sense that it decreases as strain increases, and with increasing Deborah number. So the materials that have experienced the most or the greatest reduction in pore volume are those deformed at high Deborah number conditions and to high strain. And this is significant because what the change in pore volume is really telling us is a change in pore pressure. I'll remind you that CO2 has a very low solubility. The CO2 is not being forced back into the melt in these systems. And for the most part, as you'll see, the cores themselves remained impermeable. So this relationship between volume and pressure holds pretty well. And we know that these highly deformed samples and those deformed at high Deborah number conditions contain pores that are the most pressurized. A few other observations related to Deborah number are the magnitude of strain weakening, the bubble wall deformation style, and the bubble wall shape. So these columns here correspond to points 1, 2, and 3 in this figure, and I have representative mechanical data on the top row and representative microstructures on the bottom. What you can observe is there's more strain weakening as the Deborah number increases. And we go from bubble shapes that are sort of squashed spheres to these really strange contorted shapes. Likewise, the bubble walls themselves go from something sort of planar and flat to really bent, buckled, and folded. I'll cut to the chase here and tell you that actually the thing that controls all of these behaviors, the mechanical behavior, the change in the core volume, the change in the pore volume, the magnitude of strain weakening, it actually all comes down to bubble wall deformation. And I'll show you that now through the lens of melt relaxation state. So a material deforming at low Deborah number, where the melt is nice and relaxed, as it's being compressed, the bubble walls have the capacity to respond relatively quickly to that deformation. So what they end up doing is that they'll stretch, but overall they'll maintain sort of their most stable configuration, which is to be near planar or very, very slightly curvilinear. And as deformation continues, they're able to sort of maintain that planar shape for the most part. Maybe we get 1 or 2 bent guys, but you can see overall, everything here is pretty flat. And that stable configuration of bubble walls actually makes the composite, the foam, quite stiff. And that's evidenced by the high viscosity that we actually measure. In contrast, when the melt is relatively unrelaxed and it's being deformed, it doesn't really have the capacity to respond quickly to deformation. And as a result, the bubble walls just sort of buckle and bend. And the moment that buckling happens, it actually makes the material softer and softer, and you get a runaway effect, which is that strain weakening that I saw in the mechanical data. At some point, the bubble walls can't buckle and bend any further without starting to touch one another, and that's where the strain hardening kicks back in. But overall, this sort of shape of the bubble walls makes the material quite soft, and that's evidenced again by the low effective viscosities measured relative to the relaxed foams. Folks in this meeting who think about suspensions may recognize or may have sort of bells going off in their head, because this is often the way that we think about suspensions through the lens of the capillary number. If we have a relaxed bubble, one that can maintain its favorite shape, its most stable spherical shape, The melt that tries to flow around it must deflect quite far, as you can see from these flow lines here. And so the overall viscosity of the suspension is quite high. In contrast, if that bubble is unrelaxed, if it's been deformed, the melt doesn't have to go as far to sort of deflect around it, and the overall suspension viscosity is a little bit lower. So I would argue that though they're fundamentally different materials, foams and suspensions, they can be understood through the same sort of lenses, thinking about the relaxation state of the materials present. Now, I spent a portion of this talk trying to convince you that bubble pore pressure matters for viscosity. What I've actually found is that doesn't hold out in these particular deformation regimes. So the materials deformed at low Deborah number are actually the ones that have lower gas pressure and yet higher measured viscosities. And the inverse is true for the unrelaxed materials. And I would posit that the same might be true for suspensions, but I'm happy to discuss that if you disagree in the discussion period. To summarize, here gas pressure has less of an impact on viscosity than maybe in Stefania's work, for example. And instead, the viscosity really reflects the melt relaxation state. Effectively, what are the bubble walls doing and how can they respond to deformation? And so I've plotted on here the range of viscosities I measure, and you see that it covers almost an order of magnitude, and that's solely a function of the flow conditions parameterized as the Deborah number and the total strain that I imposed on the system. The outgassing story is much more succinct, but I think equally as cool. So the objective here is to figure out how and when bubbly melts outgas. And I've already introduced a couple ways in which a bubbly melt could lose its volatile phase. One would be microcracking upon crossing the glass transition, leading to a sort of leakage or drainage of volatiles. Another would be the resorption, particularly of volatiles like water, and their diffusion out of the melt. That's another way to sort of bleed the system of its volatiles. What I'm going to focus on, though, is a much more physical process, and that's outgassing following the creation of permeable pathways. And there are two sort of prevailing models for this physical understanding of outgassing. So the conceptual model on the left is the so-called permeable foam model. And in this model, the idea is that the bubbly melt is moving towards the surface. As bubbles are growing, they connect with one another, creating a high permeability material. And that high permeability is essentially sustained through the entire period of that lava flowing across the surface. This allows for continuous passive outgassing, and at some point at the flow front, because it's had so much time to outgas, all the volatile phase has been lost, and we're left with these dense regions of dense regions of bubble-free melt that are later quenched to obsidian. And this, as I said before, is something that we frequently observe in silicic lavas in the field. The other conceptual model for physical outgassing is really a compilation of a bunch of different sort of more recent studies, which propose that thin permeable pathways are created either as a result of very localized bubble coalescence or melt fracturing. And these ephemeral pathways allow for sort of bursts of outgassing. But once the volatile phase has been lost, there's nothing to keep them open any longer. They close in on themselves and seal, and that outgassing pathway is lost. So for this model to work and for outgassing to be efficient and give us thick bands of obsidian in these lava flows, permeable pathways would need to be continuously created. So those are the two sort of end member models that exist at the moment. And what I wanted to do in my foam glass experiments was try to determine the conditions for permeable pathway formation and get a better handle on when these models work or don't work. I've already described for you my deformation experiments. What I did following deformation is that I measured the permeability of the material. And the really remarkable thing is that the majority of samples remained impermeable, despite being significantly deformed, having their total volume decreased by up to 60 or 70%. The exception, of course, are the cores that fractured during deformation. And you can see those guys noted here with X's, while the remainder of the data are plotted down here at the limit of the apparatus I use to measure permeability, which is 10 to the minus 18. So I'll remind you that fracturing only occurred in unrelaxed melts, so those deformed above Deborah numbers of 10 to the minus 2, and only at high strain, or usually at high strain. I want to show you what those fractures look like now. So as I said earlier, foam glass oxidizes when the melt encounters atmosphere at high temperature. So what we can do is take one of these fractured samples, cut it open, and retroactively see where the fractures formed. So I've got an image here of one of my deformed cores, and then a cartoon on the right showing the same features, but just a little bit more clearly. A bunch of fractures have formed down here, giving this region of green. But I want you to mostly focus on the 1 or 2 fractures that formed up here in the center of the sample that illustrate a little bit better their geometry and their thickness. What you can see from these green traces is that fractures that form, these outgassing pathways that formed during my experiments, are thin and they're near linear, and they form perpendicular to the compaction direction. This makes them compaction bands. The oxidation of the glass also shows that when a fracture forms and the CO2 is expelled and the atmosphere is imbibed and thus oxidation occurs, that's limited only to the fractures. It's not a pervasive process. We don't have whole-scale outgassing of the material as a result of fracture formation. And this really indicates how inefficient outgassing by melt fracturing can potentially be. Notably, permeability of these samples is also strongly anisotropic. So the 2 data points that you were seeing earlier are actually representative. Oh, I lost my cursor for a little bit. Here we are. Of permeability being measured along the plane of the fracture compared to perpendicular to the plane of the fracture, where the material, the core itself, again, appears impermeable despite having this fracture running through it at the center. I'm going to return now to my Deborah number figure and plot on there the outgassing regimes that I've observed based on these experiments. So on the right, I observed ephemeral pathway formation by melt fracturing. So this model I introduced earlier, and that only occurs, as I said, at Deborah numbers greater than 10 to the minus 2. But a majority of my samples remained impermeable across a wide range of flow conditions parameterized by the Deborah number. So what I would put forward is there was a previously unrecognized sort of outgassing regime wherein the bubbly melt is actually persistently impermeable and no outgassing occurs. This really underscores the fact that bubbly melts have a hard time outgassing efficiently, which contributes to more explosive eruptions, to these expansive lava flows, and to the potential for far-field explosions. So that was what I've shown you till now with the outgassing material and the rheology stuff were things that I published in 2019. I want to show you a little bit of unpublished data that I think you might find interesting. I wanted to know what happens over here at low Deborah number space in terms of outgassing behavior. So I conducted a few extra experiments, and these ones were done at higher temperatures, so lower Deborah numbers. And it was such high temperature that my load cell actually wouldn't read anything, which is why these data are unpublishable and why the core shapes are a little bit strange. But it's at these Deborah number conditions that I observe, so sort of for the first and only time, bubbles coalescing. You might, it's a little bit hard to see, but there are a lot of outsized bubbles in the center of this core here. Normally bubbles are about that shape or size. I also observed sort of large regions of oxidation, despite there being no fracturing, perhaps again indicating that connectivity was formed at these low Deborah number conditions, leading to sort of whole-scale outgassing of the foamed core. So what I would put forward to you then is that the permeable foam model may actually sit at this lower Deborah number space, and that puts all of our outgassing models on a continuum dictated by flow conditions. And really the way to move between them would be the deceleration of a bubbly melt or by its cooling. Throughout this talk now, I sort of can't get away from talking about the interplay between rheology and outgassing, but I'd like now to specifically highlight their influence on one another, even though you've heard me say these things sort of up until this point. The first and most obvious thing is that porosity loss, the loss of bubbles, pores, whatever, increases viscosity. We still don't know sort of which direction this arrow or how exactly this arrow will be oriented. That's a matter of something about geometry, something about the nature of the bubbles or pores themselves, something about the flow conditions. But ultimately, we know that any change in porosity will drive you up in viscosity. Gas loss as a result of leaking or draining can change the path that you're on in this relative viscosity porosity space, as evidenced by Stefania Secola's work and her final figure here. I didn't focus on this for the sake of time, but materials that are deforming rarely deform homogeneously. There's often a region that is a little bit weaker for whatever reason, and deformation will localize in this region. That localization of deformation locally increases the strain rate. And so what you can imagine then is that in this Deborah number space, you're moving to the right. But because there's a relationship between viscosity and Deborah number or strain rate, you're also sort of moving down and creating an increasingly weak material. This creates a positive feedback loop that ultimately will drive the material into a state where it can fracture and experience outgassing. And finally, as I've shown here, flow conditions ultimately dictate the outgassing mechanism and its related efficiency. So some take homes here. The viscosity of melts populated with bubbles are distinct from those populated with pores. And I would add too that the pore space geometry matters. And I think going forward, that's something that we need to consider when we're thinking about the viscosity of bubbly melts. That's my pitch to the community. I've done some of the first studies on melt foam rheology and volcanology and have observed that the rheological and outgassing behaviors are ultimately controlled by the melt relaxation state. And finally, I've observed that bubbly melts actually can be persistently impermeable, something that we didn't necessarily know, but the impermeability can be shifted depending on the particular flow conditions. So as promised, my final slide, which says there's still lots to do. I have a few ideas for future experiments here. I'm actually not working on these sorts of projects at the moment, but if anyone wants to team up and take a crack at them, please feel free to get in touch. As eye candy for everyone else, I have a few images here. This is a photo from Little Glass Mountain showing elongate isolated bubbles that are actually lined with a vapor phase precipitation juxtaposed to dense regions of obsidian. Really interesting, cool textures. This sample up here is a foam glass core that I compressed to 85% axial strain. And then just to see what would happen, I later reheated it in a furnace without any load on top, and it began to actually increase in length. So there's some pressurized gas in there that's exerting enough force to resist gravity and actually sort of recover some of the strain that had been imposed. Really interesting features that you can explore with foam glass. And finally, on the bottom are two XCT videos showing the difference in bubble wall geometry in foam glass samples deformed at different Deborah number conditions. With that, I'd like to thank you for your attention and ask if there are any questions. Thank you.
Thank you, Amy. Great talk.
Thank you.
As you can imagine, I have a lot of questions, but I'm actually going to park them all because I will be hugging the stage otherwise. I know we can speak at many other times.
Yeah, sounds
so I'd
good.
like to open the floor for questions to everyone that's here, present today. Don't be shy. Janine, I think you have your hand raised.
Yes, I do. Thank you. That was a really great talk, Amy. I really enjoyed it, and I always like seeing your work. So it's nice to sort of be updated on what you're doing.
Yeah, thank you.
With this study. So I guess I was wondering a bit if you could tell us a bit more about the connection back to sort of natural products. And so, and I guess I think a bit more about the kind of plumbing systems and magmas moving around before they come out, but how some of those textures that you see in lavas actually might also be present in intrusions sometimes. And so I wondered if you, what your thoughts were about like fluctuations in conditions and whether there would be any kind of record of those fluctuations in pressure or something, or whether it's only really the kind of final stage of things which is being recorded in the rock. Just wondered what you thought about that.
Yeah, I mean, as you well know, it's very tricky to unravel all of these things because they're overprinted on one another. But it does seem like in the last, 5 or 6 years, we're using a combination of things like there's a great paper in 2019 using chlorine and water diffusion profiles to essentially recover where permeable pathways had been by the differential diffusion of those two volatiles. Using something like that, in addition to texture, in addition to sort of our understanding of things like the viscosities that we need to get the material to the surface, I think will begin to sort of allow us to get better insight into what's happening in the subsurface. But yeah, as you acknowledge, it's quite tricky. And unfortunately, I don't think that my experimental results necessarily lend themselves to as tools to sort of unravel what's happening in some natural materials. But for example, in lavas, that image there of the little glass mountain lavas here, those textures are extremely similar to what I observed in my silicate melt foams, in that the bubble walls are preserved in that foamed area, despite that being, kilometers from the vent and right next to a region that had lost all of its volatile phases. So I don't think that necessarily helps so much with the question, so much as, yeah, I agree with you that it's quite complicated.
That's really interesting. Thank you.
Good. Next question, Jenny, hands up.
Hi, Amy. Thanks for the great talk. I was wondering, because you are saying also in the ideas for future work that you want to do experiments on foams. I guess that means you want to do experiments on foams with water or water vapor instead of CO2. And what would all the results that you showed from the foams experiments, how much do they actually, how useful are they to interpret then natural textures? Because I guess it does make a difference, right? If it's water vapor or CO2.
Yeah, absolutely. The fact that a foam that would have bubbles populated with water versus CO2 will be so responsive to changes in pressure and temperature, you could very quickly, the material itself might look exactly the same as my CO2 foams when they're deforming, but in cooling, we would lose any sort of record of them being foams to begin with. Yeah, ideally, it would be really interesting to try to work on a foam populated with water-filled bubbles. I mean, the way that we know to do that right now is taking something like the Crofla obsidian and heat it up and hope that we get to the right range. But obviously from Stefania's work and from work that you all have done and I have done, we know that's not the most easy. So I think a different direction to go might be to use the CO2 filled foams as a starting condition, and then use modeling of water solubility to begin to understand how quickly those textures will be erased and how quickly you'll change the viscosity of the material. That seems like the most feasible way to do it. But I don't know if anyone else has other ideas there.
Cool, thank you.
Yeah.
Okay, next on to Dan, Mr. Faulkner. Floor is yours.
Thanks, Jan. So yeah, really nice talk. So thanks for that. I had a couple of questions. So one was just about the barreling of your specimens. I think you said a little bit earlier on that the diameter didn't change that much too, but I just wondered whether you did account for the change in diameter with strain in there as well, because obviously just a 40% increase in the diameter will double the area. So
yeah, I did I would measure the change in the diameter of the samples before calculating the viscosity. Oh, I've gone back too far now. There are equations by Ghent for uniaxial compression of experimental materials where you account for the perfect slip or no slip conditions, which would be changes in the diameter as a function of deformation. Those equations are a little bit difficult to work with in these sort of porous materials because there's a difference in the actual contact points. But it seemed to work out relatively well. But yeah, I did think about diameter. I didn't ignore it, but I just ended up seeing that in many cases, particularly at high Deborah number, the diameter wouldn't change. And so I think I almost exclusively used, I forget now, the no slip or perfect slip formulation there.
No, that's okay. It's just with the strain hardening. So that's real strain hardening, not just apparent. Yeah, so that's cool.
Yeah.
And then, yeah, I mean, it's an amazing result really with these foams that you can deform those and they stay impermeable too. So I just had a speculation question, I suppose, on that. Do you think that the pores there or the bubbles connect and then kind of reclose? Whether there's evolution, whether there is kind of transient connectivity that you get between these, or does it just really stay completely impermeable and there's no transfer of during deformation?
Yeah, I mean, it's a bit hard to say. As you can sort of see from my mechanical results and from these experiments here, I've conducted experiments across a range of strain and then looked at how the microstructure evolved with strain. So I don't see a marked change in bubble size or bubble shape that's sort of out of the ordinary and would lead me to think that bubbles were becoming connected during deformation. I would also sort of imagine that it would become a runaway effect a little bit if particularly at high strain, if I'm getting really significant pore volume reduction and thus increased pore pressures, you'd imagine that any sort of perturbation of the system, some small drop in pore pressure from two bubbles linking up would have the runaway effect of essentially making a fracture propagate outwards. And maybe that's actually how my fractures are starting and propagating, is from one bubble wall failing and then everyone around it sort of responding in kind. But in the viscous flow, I don't necessarily think that that's happening.
That's great. Okay, thank you.
Yeah, thanks.
Anyone else for question? Don't be shy. I'll have a quick one in passing.
Okay.
Actually, will that be about the bubbles? Because I would have a lot of questions not about the bubbles. But about the glass, obviously you saw the glass oxidizing when fractures develop and then you have an oxidation that takes place. Did you manage to map what happens to the glass? Like if it crystallized, do you find nanolites inside or?
I didn't observe nanolites, but I actually didn't look for them either. So I never did any sort of XRD analysis on these after the fact to see whether those had formed. And actually all of my imaging was in sort of secondary electron mode because of how difficult it is to prepare these because they're so fragile. So I ended up, I never looked for it. Maybe there's a possibility that there has been some crystallization in the soda lime itself. I kind of don't think that's happening, but I never looked, so I don't know.
Okay. Good. I'll just throw another one in there then. Just actually, it's more like a comment for comparison. Maybe like a few years ago during a discussion with Becky, I don't know if you talked about this, but one of the things that Becky had done when she was in Liverpool is looking at essentially the peak stress region experiments of when she deformed lava with vesicles. Her lavas had crystals in them, quite crystal rich. And one of the findings we had, and I was very surprised by this, she saw essentially no peak stress or viscosity change as a function of the vesicularity between about, I'm looking at the graph now, about 12% and 28% porosity. It's quite a wide range of porosity. And we saw no change in the viscosity. And we sort of speculated maybe it is that you have that good drainage, it's extremely well connected pores. This is all connected porosity, those values. And maybe eventually the presence of crystal in the system, in the suspension, eventually sort of takes over, perhaps.
Yeah. What were the crystal contents?
High, let's say 70-80% crystals. So it's quite high.
Yeah, in that case, so this is sort of more drawing on what I'm working on now. I'm working on suspensions that are 40%, 60%, and 80% crystals, and there's no bubbles present. But I'm definitely running into the condition when you get up to 60% that really any mechanical response is about the interaction of crystal and crystal. So it doesn't really matter if it's melt, or I would posit doesn't matter so much whether it's melt in between them or vesicles, because you're really just seeing the effect of the crystals, and it doesn't matter what's in the intergranular space. But that's just sort of a rough rheological division, and perhaps depending on the crystal shape and size, there could be a significant effect.
Good. Any more questions? Well, if not, then I'd like all of us to thank our speaker. I think Amy did a fantastic job there. It's very interesting stuff.
Thank you.
Great work. And we all do need to speak more, definitely, about what can be done.
Yeah, that would be great.
We will. Good.
Thank you.
Okay, thank you. Caitlin.